on this computer, sure. Can I get it? Yes. Okay. Cool. Welcome back to everyone who was here last week. Hi to everyone on the recording. And a very quick summary for everyone who wasn't here or needs reminding. Last week we were going through a Back to Basics Jupyter notebook that I've been hosting on Colab. So this one is a different version from the one that I would have shared last week because frankly I'm not very organized about how I transfer stuff from when I work on it locally, like here, when I transfer it to Google. I need to think of a better way for doing that. But anyway, it builds off an early tutorial that we did called Basic Bits Python, which covered a couple of simple Python primitives like strings, dictionaries, different types of numbers, and so on. And it culminated in translating this amino acid sequence from some DNA. I've left some info in about the amino acid sequence, the protein that we're looking at. And then we spent the first half of the session using this table, which contains properties of all 20 natural amino acids. And yeah, we were trying to work with a copy and paste of that table, which does sometimes happen. Sometimes you might be on the internet and you copy and paste some data in, and it might not necessarily be in a format that is especially easy to use, like for example this one. So we made a multi-line string which we needed to do some work with to clean it up. So we split it by the new line and the tabs characters. We also looked at the easy and recommended way to process it into a pandas data frame using the string.io module. Then we spent the rest of the session going through that string and breaking it down into lists and then dictionaries, and then a dictionary of dictionaries, which contained each amino acid, and within that a set of their properties. I'll tell you what I'm going to do. I'm going to go up to the first code cell and use Shift-Enter to start running them, just in case one of them depends on a previous one, in which case then everything should be fine. Okay, and we had a couple of exercises, and I think we stopped at around about the point of around about where we had our dictionary of properties for each amino acid, and then we had to, number one, use those dictionaries, or the dictionary of dictionaries, to find the number of aromatic rings, which is one of the properties in here, in the amino acid tryptophan, which is designated by a capital W. And any answers I left in this file, which in this cell I download using Bash rather than Python, but we'll get to that later. So anything that you don't manage to do, it should be okay. You can always have a look at the answers sheet if you like. Okay. Did anybody get as far as exercise number 6? I think that's where I'll pick this up again. Does anyone remember that? So the aim of the exercise was to use the dictionaries that we'd made, or a dictionary of dictionaries, to find the total molecular weight of the protein designated by this sequence up here. So this was copied and pasted in again from a few cells above. And there are a couple of steps involved in solving this. Number one, we needed to save this sequence as a string, which is sort of, I guess I already did that. And then after that, there are some characters that need to be replaced, particularly the \ns, which aren't in the dictionaries that we just made, so that will throw an error. And also this star at the end. Does anyone remember what \n means? \n means a new line. It's like an enter. And the star at the end isn't a computer specific character. In this case, it's just designating that that's the end of the protein. Okay, so we'll kick off this exercise with, we'll kick off this session with finishing exercise number 6. So if you've run the cells, then you should have this variable D, which should be a dictionary that contains all of the amino acids, all 20 letters, and each one of those has a dictionary inside it that corresponds to various molecular properties, like, for example, this molecular weight, the number of aromatic rings, and so on. Actually, I suppose as a warm-up, let's do this exercise here. Find the number of aromatic rings in tryptophan. I'll walk you through that, and then hopefully you can apply that to the exercise below. How's that sound? Okay, so very briefly, you can look up items within a dictionary by using square brackets and then the name of the item. In this case, the item we're after is W. And there we go. And then here's the dictionary that then corresponds to the amino acid tryptophan, which has the symbol of W, which is a little counterintuitive. The next task was to find the number of aromatic rings. And we can find it just by looking, but for the sake of demonstration, and this will come in useful in the next exercise. So because this D looked up by W has returned another dictionary, we can look up again inside that dictionary the value that we want, which in this case, we're looking up aromatic rings again. So that's how to handle looking up features. So that brings us on to exercise number 6. So the aim is to, number 1, clean up the sequence using things that we might have learned in the last tutorial. And then number 2, loop through the sequence and for each letter, look up the corresponding molecular weight and sum up those molecular weights, and then add 616.5 to it to account for the heme ion, which is a sort of non-protein group that's sort of part of the protein. And that should give us the rough molecular weight for that. So I'll start a timer for us now. I think a 5-minute timer sounds okay. And if we need more time at the end, then so be it. Okay, off you go. If anyone has any questions or anything that needs clarifying, then feel free to ask either in the chat or out loud, though I might miss it if it's in the chat because I don't always see it. Good question, Steve. Do you need to account for the H2O loss when the peptide bond formed? For the purpose of this exercise, no, but well observed. I definitely forgot about that. Yeah, just the sum of the corresponding dictionary values for each amino acid. Yeah, question. What's your question, Fatana? Am I saying that right? I can't hear anything, so maybe it's a microphone problem. Perhaps try pasting it into the chat. We're getting there. How's everyone doing? Why we set a timestamp? Would you mind elaborating on your question a little bit, Fatana? Timestamp in what regard? Are you looking at the same bit that we are? Section 6 up here. What do I say timestamp? If you're referring to this line here where I talk about timestamps, I'll come on to that later. Okay, let's go through the answer in the meantime. So step number 1 was to remove the \n characters and the star characters from this string variable s. So let's look at a couple of ways to do that. One way to do it is to create an empty list with a name. Let's call it S2, why not? And then go for a loop through the string s. So for letter in s. And then we can use an if statement if we want. Yeah, it's just occurred to me that this is a terrible way to do it, but I'll keep going. If letter is not equal to backslash. No, this isn't going to work very well for me. I think it's possible, but I think I'm going to ditch that. I'll use a string method instead. S.replace, and I'll replace the string \n with an empty string with no space. Let's try that. Okay, that worked fine and took up much less space. All I need to do now is to remove this star on the end. So what I can do is even put replace onto the end of this. So s.replace, and this operation evaluates to another string, which means that I can do another string operation on it, like this. Alternatively, I could just save it as a second variable, like for example, s2 is equal to s.replace, and then on a new line, s2.replace star. That's a little bit clearer, so we'll go with that for now. Okay, and then the next job was to go through each item in it and look up on the dictionary what the molecular weight for each amino acid is. Steve quite rightly pointed out that it won't be exact because when these things are joined together, there is a water molecule that's released, which is an oversight on my part. I didn't actually think of that, but yeah, that's true. But anyway, for the purpose of this exercise, we will go through. So similar to how up here we used a double lookup to get our number of aromatic rings, we're going to loop through each letter in this string and look up the letter, and then from that dictionary that will return, then look up the molecular weight. So let's do that. So we have our clean string S2, so we can go for letter in S2 and colon and an indent. And now the properties dictionary, let's call it props, is equal to S2 looked up by the new variable letter. So in the first iteration, this variable letter will be equal to M. Sorry, look up the dictionary D by the letter. And let's print props to see what that looks like. There we go. So that's each dictionary for each letter for the whole thing. So within that, now we just want to locate the molecular weight of each one. So let's try just printing out the molecular weight of each amino acid. There we go. That's looking more like it. So now all we need to do is to store these molecular weights somewhere, and so that we can sum them all up after and then add our 616.5. So I'll make a new variable, well, WT is equal to the lookup of these properties by molecular weight. Now, where do I save them? Well, one thing I can do is to make a temporary list called temp, but you can call it whatever you want. And then within the for loop, I can add the molecular weight to the list with temp.append with one bracket and mol WT. Okay, now let's have a look at what this new list temp looks like. Okay, so it's all of the molecular weights that we have found with our dictionary, all in one list. One easy way to get the sum of it is to use the Python built-in sum function and run it like that. That's definitely the easiest way, but if anyone else found another more creative way, I'd be interested to know. I suppose you could, rather than have a list up here, you could have had more weight equals 0, for example. Let's comment that out. And then rather than appending temp to a list, we can say more weight plus equals. So the plus equals operator basically updates this variable, which starts off as 0 in the first iteration. It in place adds to it whatever the molecular weight is. So that's another way of doing it. So let's have a look at what that evaluates to. Okay. Are they equal to the same thing? They might be, if I can get my syntax right. No, they're not. Okay, that's strange. I kind of want to know why that is. My suspicion is that because it's to do with the precision of floating point numbers. Let's print them both out and see what. No, okay, so it's not because of that. Okay, can anyone see the problem in this loop? It's stuck out to me here. So the problem is that I haven't been very sensible with what I've named my variables, and I'm trying to do two things at once, and I've sort of crossed their wires a little bit. So on the one hand, I was taking the approach of adding the molecular weight in each iteration to this number here that starts at 0, which is fine. And then in the other approach, I was adding the molecular weight to this list that I would then take a sum of later. The only problem is I reused this molecular weight variable, which increases each time by the molecular weight. So it's a large number. So the way around that, so I could have it find the dictionary value twice. That's what I'll go for now, because just because. Here you go, now they're the same. The other thing I could have done is made a more sensible variable name here that doesn't overlap with the other one. Okay, did anyone have any trouble with that? Can anyone tell me what I've forgotten to do? Steve, to account for the water lost, n equals len s2. Okay. I don't know if anyone else saw Steve's message in the chat, but he had a pretty neat insight. So let me paste what you wrote in. So I suppose this wouldn't go in the loop, would it, Steve?
After the loop.
Yeah. So n, I suppose, is the number of water molecules that we're losing, right, Steve?
N is the length of the amino acid string.
Okay.
So it's the number of amino acids.
More weight equals more weight minus 1.
And they're going to be n-1 peptide bonds.
Okay. And then times the weight of water, which is this.
Presuming
okay.
my Google lookup is okay.
Yeah. Well, let's assume that. Let's go for molecular weight plus equals this. Let me get rid of all of the temporary list stuff. Okay, that looks all right. I think the only thing that I haven't done now is add the 616.5 to account for the heme. And there we go. I suppose it's worth noting though that maybe there'll be a slightly different number of hydrogens on, or something like that. If you didn't manage to do those exercises in your own notebook, then run these cells. This imports the answers from this file back to basics, which we downloaded in an earlier cell. It's important to note that there's not one answer for most problems. Normally there's a few options available. So this function that we import gets rid of the \n and the star characters, and this one, find molecular weight, that just does the dictionary lookup minus the plus the heme and minus the accounting for the waters that we've lost along the way. So in this expression, I input into this find molecular weight function the answer from another function that we import up here, and I also input the dictionary. So that's what's going on there. Okay, now part 2. I think I need to find a good sequel title for part 3 when part 3 happens. So the aim of this session is to introduce you to some simple bash commands and maybe briefly explain what on earth bash actually is. We'll use that to download some structural data of our protein that we're working with from the internet. There we go. We will open the file with some built-in Python commands and then use some of the string operations that we've learned in section 1 to get the useful information out, which in this case, I want to know about the atomic coordinates. And then I sort of run out of time on this last point, so we'll see how it goes, but then we'll be putting this data into a pandas data frame, which is a sort of a table format, which is quite easy to work with. Well, anyway, onto bash. So bash is a shell scripting language. If you have a Linux or Mac computer and you've ever opened the terminal, then bash will be the default language that you'll be interacting with the operating system with. It's worth noting that these Colab notebooks are hosted on Linux servers somewhere, so they'll also accept bash. I've got to say, if you run these notebooks on Windows, I don't know if these bash commands still work. So I'll be interested to know if anyone has any insights. The advantages of bash is that you can do quite a lot with little one-liners. They're quite high-level commands that let you do some quite powerful stuff. So I'll give you some examples of some today. First of all, I should explain that the ways to invoke bash are, at least in these Python notebooks, is to start the line of your code cell with an exclamation mark, and then the interpreter will automatically detect that it's not Python you want to run, it's bash, and it will interpret it as bash. Alternatively, if you'd rather have a multi-line bash script, then it might be more practical to put in %% bash at the top of the cell, and then you can type as many lines of bash as you want without having to worry about prepending your code with an exclamation mark each time. Here are some useful bash commands that you might use to mostly navigate file systems, actually. ls lists the directory contents. I think I can show you with, let me get out of Steve's server. So here's an example of my terminal. So the folder that we're in is in the Python Club tutorial section, which should be a pretty decent mirror of what you might find on the GitHub page if you've ever looked at that. ls will list us all of the files and the content. pwd, print the working directory. In this particular shell, we already have it available to us, but in the Colab notebooks, we don't. So if we want to know what folder we're in, then that's a useful command. CD for change directory. So it's worth noting that this Python notebook has started in a particular folder, but it's possible to sort of move where we are, if you like, or at least where the interpreter will think to find files and so on. We can remove files, move files, show the contents of them, make folders, and crucially for today, we'll be using the wget command, which pretty much just downloads stuff from the internet and then saves it as a file in your local directory. It's worth noting that a lot of bash commands have options on. So we'll take the ls command again. So by itself, we'll remember that it just listed out our files just like that. But if we add ls.-l, then that invokes extra options for this command. Most bash commands are pretty similar in that regard. You add a, people call it a tack, but a dash, people will know what you mean. And then it adds extra options. So the L stood for long format, and now we have extra information about all of the files in the folder. You can also string them together, like for example, H for human readable, which will make the file sizes more human readable, and so on. If you ever need help with any bash commands, then one way to do it is to type the name of the command and then --help. And usually you should get something like this that will explain all of the ways that you might be wanting to use this command. There are other ways to find out what bash commands what a bash command might be capable of. But for now, we'll leave it there. Okay, so now the ball's in your court. So I mentioned this command wget. And we want to use wget to get to this file here from the internet. So the first steps are, number one, in this cell, find the help page for wget. It should give you an overview of what it does, what it's for, and the options that you can have with it. Then after that, I'd like you to use wget to download this file from this HTTP link. But download it into the Colab notebook. Well, you can download it into your local computer if you want. Then after that, for extra points, you can find out what your current working directory is called and then list the contents of the folder that we're working in at the moment and see if there is a .pdb file in there, which should correspond to this one here. Okay, your timer starts. Thanks, timer. Now, go. If anyone has any questions, then feel free to ask. Okay, Steve has pointed out in Windows, the exclamation mark calls Windows commands rather than bash commands. So if you are running this notebook locally in Windows, then unless you install wget, it probably won't work. And if that is you, then probably the easiest way to do this is to just go to this link and then let it download to your computer and then just save it to wherever your notebook is. Okay. if you're having trouble with exercise number 2, then there's a clue a little bit further up towards the end of session 1, where we use wget to import this file, or sorry, to download this file, which contains all of the answers like so. Does anyone know any better countdown timers than the countdown timer? We can use it for now. How's everyone getting on? Is 5 minutes enough? More than enough? Okay, I'm just going to start the countdown timer. Cool. Okay, let's see what we've got here. So find help for wget. We had a couple of options. We could have either started by appending your command with an exclamation mark and then gone ahead with wget --help. See if I can stick my L key back on. And then running that should print out this, which has quite a lot of options because it's a fairly well-developed tool. You'll notice that the -h rather than --help is a shortcut for --help. So sometimes you can use that to help yourself sort of deduce what commands might be what. One of the key parts of this documentation, apart from all of the additional commands that you might want, are the usage bit at the top, where you have the name of the command, the optional arguments, which are optional, but they will come before the URL, and that's it. So say we were to do this in the terminal. Well, we can do it either way. wget, and here is where maybe some additional options might go. And then you run it and it will give an output a little bit like that. So it will automatically connect to the server and then create a file. And it will also detect if that file already exists, or at least that file name already exists, and assign it 0.1 rather than a name that's already been used. So let's try that here. The other way, rather than prepending with an exclamation mark, could have been %- at the top of the shell. And I suppose if we want to avoid all of the extra text that wget generates, then we could have -q for quiet, as per here. And then after that, to check that the file is in our current directory, well, we can print our working directory first with the command pwd, and then that will be followed by a list of everything that's in the directory. So let's see what that does. So this didn't put an output because we quietened it. We printed the working directory, which is called /content. And then we listed the directory, which contains a few copies of 1bu7, which is the file that we're after, and also the second time that I downloaded it. And it looks like I've downloaded the answers file twice to there, so that's good. If you didn't manage that, then I've implemented pretty much the same sort of thing in Python, which uses the request module to do pretty much the same thing. And if you execute that cell, then we should all be on the same page, which leads us on to opening the files, which is another built-in Python command. So there are a lot of packages and modules in Python that have functions that allow you to open files and so on. But they will often revolve around the built-in Python command open. This is like the original, the OG file opening command. So the syntax looks like this: open, the file name, and then separated by a comma, you have, at least in our case today, R for read, W for write, and A for append, which means to add on to the end of the file. So this function returns, or opens the file and then returns a file object, which has a few methods associated with it, including read or write or append. But in today's examples, we'll mostly be looking at read and a little bit of write. So here are some options, or sorry, an example of what it might look like in the wild. So if you were to run this command in a code cell, then we would be creating this object file, which would be the file handle object of the answers file that I've included in the notebook, and would have it in read mode, which means that we wouldn't be able to write to it, but for the sake of reading it, that's fine. So then I print this file object, and rather than printing me the contents of the file, it prints me the type of the object, which is, well, an IO type object. It has a name, it has the mode, read or write, and it says encoding UTF-8, which maybe we'll cover another time. And then to get the contents of the file out of this file object, you can call the method .read out of this file object, and then it should print something that looks a little bit like this. And the only thing left to do after you've extracted the data from your file is to close it. Reasons being, more through this link here to an answer on Stack Overflow. It frees up some RAM. You can't always guarantee that the Python interpreter will close the files after it itself shuts down. RAM being the short-term memory of your computer, which is a fairly finite resource. Any changes that you make to the file, if you're writing to it, might not be actually made until the file is closed. So you might not make the changes that you think you've had. And other programs might not be able to access that file. Like, for example, say I have another Python program that is running at the same time that needs to do something with this file. This is a problem that I have quite often. Sometimes it will try to open the file, it won't be able to, it'll crash. And as a result, then I might find out the next day that I could have reclaimed a couple of hours. Also, antivirus tends to need to open the file so that it can scan it for viruses and so on. Okay, we have an exercise. Can I remember what it is? Okay, yeah, so this exercise is to I suppose you'll need to create your own code cell somewhere. If you hover your mouse around the middle there, there's a code button here. This exercise, you are tasked with creating a function that prints Python is the best language 100 times. And because that is a useful function that we might want to reuse, you'll be wanting to wrap that function as a string and opening a file called whatever you want and write that text to a file and then close it after. I suppose the key part of the exercise is to get some familiarity with opening, writing to, and closing files, and also reading it. So I suppose it's not essential that you actually make a Python function. Any string will do, any file name will do. I'll start a slightly shorter timer than last time because I'm a little conscious that we're coming up to the hour. I'll give us 2 minutes and then go through it quickly. If anyone has any questions, then please ask. And then after that, maybe we can snap up the last couple of exercises, maybe before 10 past. Sorry for overrunning again. Okay, let's time that before that goes off as well. Okay, quickly I'll go through the answer. Hopefully no one had too much of an issue with it, but if you did have an issue, I suppose we can talk about it at the end, and I don't think the future exercises depend too much on this. So let's make a string first. That will be our file contents. It'll be, I'll write this function, def, give it a fairly generic name, and for I in range 100. Python is the best language. Steve has pointed out that there's a wget Python package, which I wasn't aware of. That could be quite useful. I think I'll take a look at some point. Okay, so in this exercise, we have made a horrendous function that prints out over and over again, Python is the best language, and we want to write that to a file. To do that, this first has to be a string, so I'm going to wrap that in triple quotes, which is the way to make a multi-line string. And I'm going to give it a name as well. I'm going to call it function. Okay, so now if we print out our function, this is what it should look like. You'll notice that all of the indentation that we took for granted is being replaced with new line characters. Well, the indentation hasn't, just the new line characters. Okay, so now we want to open a new Python file. Python files are just plain text files. There's nothing magic about it. So let's give it a name, new function.py. Adding the .py at the end is more for humans to know what it is. It doesn't endow it with any special properties. And we'll be wanting to open this file in write mode. This should return an object that I'll be wanting to name file. Okay, file equals open new function.py in write mode. Okay, now I can file.write and I can paste in our function or the alias to the string of the function, and then file.close. And there we go. So now if we use some of the bash commands that we learned earlier, ls, for example, which should list the current directory, we can see that there is a new function.py. Oh, you might also notice that I didn't actually put an exclamation mark here this time, but yet it still was recognized as a bash command. Some of the more used bash commands, the Python interpreter will just kind of know what you're doing, but not all of them. Okay, say we want to see the contents of this file. The bash way to do it is with the command cat. And we can see it has the expected contents. But say we want to do that with Python. File, let's call it new file. Why not? Equals open .py, and we're going to be wanting to open it in read mode rather than write mode as we did last time. Let's print out the contents of the file. So that will be new file .read is one way to extract the information from it. And at the end, then we'll be wanting to close the new file. So new file.close. And there we go, the same output as with the bash commands. So there we have it, simple writing to a file. Okay, before we finish, I thought I'd mention the context manager. I've left a couple of links in here in case you want to dive into it a little bit deeper, but the recommended way of opening a file is to use the with context manager. So you'll notice that the syntax is pretty different, but it comes with a few benefits, namely that by typing your file operations like this, you don't have to remember to close it, which is a fairly common problem. And also errors in opening and closing the file, etc., will be handled for you. So the syntax for using the context manager is with, and then the same command as we would have used before, open back to basics in read mode as F. So whereas before we were saying, well, we'd be saying F is equal to open this, it's switched around. So with this as equal to this, and then within the indented block, you do all the same operations that you ordinarily would. And then as soon as you leave the indented block, then the file closes down automatically and cleanly, and any errors are handled. So that's the recommended way of reading a file. Okay. Okay, before we finish, I will talk about, I'll go through the data that we downloaded, and then we will also sorry, I'm dragging boxes around the screen, not really knowing how to fix it. Okay. Okay, so a few cells up, we downloaded our PDB file named 1bu7.pdb. And one option to extract the data from it would be f.read, which in this case we're doing within a context manager, but it's still acceptable to open and close it as before with .open and .close and so on. Sorry, no dot, but at least not before open. Another function available to us is read lines, which, as it might suggest, it returns each line in the file, text file, separately, all bundled together as a list, like that. So it's detected each one is a different line. So this can sometimes be an easier object to handle than one big string that includes all of the data. At the bottom of this cell, we've printed the length of this list of lines, and we found that it's just a shade over 9,200 lines. And I've left some information about the sort of file we're dealing with. So you might remember at the top of this notebook, there's a 3D structure of a protein. And this is the file from which, well, the file where the 3D structure lives. PDB files are quite strange, and a lot of it has to do with their history. They have, so they're text files, and if we print out various ranges of lines within them, we'll see that inside that they have some info at the beginning, like the title and so on. Then we have the sequence of residues, is what secres means. Essentially, it means the amino acid sequence. Then we have some more sequence, which corresponds to whether or not this particular part of the protein is either in a helix or a sheet conformation. If you're interested in finding out what that means, I've left links up here, but it's to do with secondary structure. And the bit that we'll be interested in, particularly in the next tutorial, will be the atom coordinates. So it's denoted by atom at the start of each line. There is the ID number of each atom. This letter indicates the element, but also it can tell me extra features. Like, for example, there's some recurring carbons in the backbone of the protein that are the same in all of the amino acids, called CB and CA. So this column sort of points that out. And here we have some three-dimensional coordinates, which is particularly what we're interested in. So this cell prints out ranges of lines that I've sort of manually fished out of this particular file. There's this isn't like a magic formula that will work for all PDB files. And then in the next tutorial, we will go through that data. We will take a look at filtering out the non-atom residues, and then we'll start bunging these things into a pandas data frame. We'll go through a couple of operations in that. And then we'll start looking at bond length and seeing what sort of patterns actually make up elements of the secondary structure of the protein. And hopefully it should be a nice insight into not only pandas and maths that you can do with Python, but also the package SciPy, which is pretty much endlessly useful. And then also, if you're not familiar with PDB files or protein structures, then hopefully this will be a nice insight into some structural biology as well. Okay, so that's all I have for today. Steve in the chat mentioned that there's a %% file magic for writing files. I've got to admit, I'm not massively familiar with the magic commands, but in short, the %% like what we did with bash earlier, is what's called a magic command. And Steve, you say that there's one for writing files.
It needs file name after the magic, and then the contents of the cell is what's got to be written.
Okay. So say I've got tmp.text or something like that, and then I can just write whatever I want. Does this need to be?
I believe so. I think that's right. Yes. I will probably have to check the definition. Oh, you forgot the file.
Oh, yeah. Okay, and then if I look at the contents of that file, there we go. Oh, brilliant.
That's a handy, quick way of writing stuff. So if you're writing a function library or something, you can do it there.
Oh, that's good. Yeah, thanks, Steve. That's interesting. Okay, cool. Does anyone have any questions over any of the material that we covered today? Feel free to ask as and when you think of them. Thank you everyone for coming. Next Python Club will be next Friday at 12. As I said, we'll be going through the data that we've just downloaded and start doing some maths and some sciencey stuff with it, which should be quite good fun. Thank you to Ying Ying, who pretty much organizes this now, which is pretty fantastic, and means it takes some work off my plate, which is good. Thank you, Steve, for useful input. That's good. Fatana, sorry I didn't get to answer your question. If you want to re-ask it now, then feel free to. And I think the only other thing I wanted to say was, outside of Python Club, in my own work, I'm working on a software. It's a wrapper for some protein structure prediction and then molecule binding simulations, if you like. Docking is called. And I've been trying my best to sort of hide a lot of what's going on under the hood away and make the interface fairly simple. And I need some brave testers to help me find the bugs. So the task would be, we'd take a file, like a protein structure file, like what we dealt with today. We'd use that as a template. We'd make some changes here and there to whatever you want, and then simulate the binding of a particular chemical into the binding site of that enzyme. So I developed this to try and automate that process, and then eventually plug in some clever algorithms that will actually hopefully evolve us better proteins. But so far I'm in like a version 0.1 of this software. So it'll be nice to have some input or feedback on how usable it is, what it doesn't do very well, and so on. And if it makes sense. I think it's one of those things where it makes sense to me because I've been sitting down writing it, but what really counts is if it makes sense to other people. So if anyone's feeling brave and wants to help me test some of this, then yeah, please let me know. Before we finish up, are there any last questions? Okay. yeah, if you're interested in helping me out with this, I'd greatly appreciate it. Send me a message. If you have any questions about anything we covered today, then send me a message. I should be around all afternoon. Thank you everyone for coming, and I will see you all next week.
Cheers,
right.
James. I'll have a
Cheers.
look at that.
Thank you.
Thanks, James.
Nice. Thank you, everyone. Yeah, if you want to take a look at that enzyme package, so it's on a private Git repository, but it's on the, I'll show you where it is on the server.